Good morning, everyone. Thank you for joining this session of Spatial Talks. Today, we will be talking about 3D digital geo-twin simulation and predictive modeling. This is a very upcoming field, and digital geo-twin and its possibilities in uh, simulation and modeling knows no bound. So we have on our panel today two speakers, Mr. Danny Savla, who's the Senior VP Genesis International, and Ms. Priyanka Talwar, who's Research Associate IIT Mumbai. So let's start with our first speaker, Danny. So Danny, he is a Senior VP Technology at Genesis, and he's primarily responsible to redefine Genesis as a dynamic and innovative technology-driven enterprises by leveraging emerging technologies like artificial intelligence, machine learning, IoT, data analytics. Uh, he has an experience of more than 15 years and worked in a mix of services and product industry with a focus on operational efficiency, product quality, and applied technological advancements as catalyst for growth and expansion. With a master's in data science and engineering, he has successfully completed leadership program from IIM Kolkata, and in his goal to drive innovation, has authored quite a few patents and white papers. And he is associated with geospatial domain for more than a decade and currently focusing towards bridging the intersection between geospatial and environmental ecosystem. He is also pursuing his PhD from IIT Mumbai uh, while doing all these things. So over to you, Danny.
Thank you, ma'am. Thank you for your introduction. Thank you, everyone. A very good morning to all of you. I will try to share my know-how of what the digital twin is and connect here in the space of the digital geo-twin. So briefly to the agenda, I hope my screen is visible to you all. So the agenda is quite simple, and we'll try to keep it as simple as we can. So first, of course, what is a digital geo-twin? It's a buzzword for sure, and a lot of definitions have come up. Talking of maturity models of the digital twin, then we have Priyanka, who will be talking about the prediction model and about simulation. Yeah. So getting started, digital twin, the origination was in 2002 lecture at the University of Michigan. And I think many of you all would be knowing it was redefined by NASA in 2010 during the Apollo mission. So the digital twin has gained its presence in the industry 4.0. I think we all know we are in the industry 5.0 era now, but it gained its popularity and ranked upwards in the industry 4.0, where we brought in the understanding of the physical system and assets together, right?
Danny, you got muted.
Oh, can you hear me now? Hello?
Yes, yes.
Yeah, sorry, I don't know. Probably mouse click. My apologies again. So I don't know where did I was last muted. So I'll start from the digital twin definition. That is, a digital twin is generally defined as a virtual representation of the physical objects, and it leverages the data. Now, this is where the confusion and the fun is, and the crazy line that needs to be drawn. That if I have a visualization of anything in the 3D space, is that a digital twin? Is that enough to be termed as a digital twin? And the answer is no. So the essential elements of a digital twin are three aspects. The first one is, of course, the real world entity or the process. And then how would I go about building a virtual representation for it? Now, so far, so good. It is a good 3D model. But to call it a digital twin, the key bridge is the connectivity and the interoperability between the two systems, which is the physical, real world, and the virtual representation. So this effectively builds up a digital twin. So this is a very fundamental definition, and being a being a buzzword, it has not been clearly articulated as it should have been, right? To be speaking from an industry standpoint, even digital twin in the industry is used in many different forms, and it is basically depending on the portfolio of the industry. The digital twin is tweaked, right? So that is the aspect of digital twin that comes in. The other thing that I wanted to call out, and now you have realized that we're talking of interoperability between the physical and the real world. We're talking of monitoring. And when I'm saying that I'm able to, exchange data between the two systems, I'm talking of being interactive. And of course, do we want to stop there? No, we want to move forward while we are in the field of artificial intelligence. We also want to have the decision-making capabilities. So defined in the literature, it is very clearly called out that digital twin is just not a technology, but it is more of a concept that pulls together several existing mature technologies like artificial intelligence, Internet of Things, and big data. And this essentially brings in, to the definition of a digital twin. And I have a very, oversimplified bird's eye view where you could see that you have the physical world, and there are a lot of the environment, the objects, we ourselves as people in the environment, anything and everything that you see in it through communication connected with the digital world, which is on the right hand side, right? A very important aspect that needs also to be called out in this is the standardization and security. You know, especially in Europe and US, there's a lot of focus on privacy, data privacy. Uh, I think India, we are getting there. We are getting our policies in place, but now we are always open to give our data for free apps. So there's a little thought process in security, but a very important aspect of the digital twin is also the standardization of data. And when I say standard of data, what I mean is when we use different kind of sensors, right? We can use sensors for air temperature monitoring, for number of people on the road, or we're looking at the moisture, or we're looking at air quality. Every sensor, every actuator will have a different unit, will have a different frequency, and will have different information being thrown at different intervals of time, and how they would be used, which warrants for us to have a standardization and normalization of the data, and also defining an ontology of how the data needs to be used. So with that said, I will now take you quickly into a new term. The new three alphabets that I've added into it is the digital GeoTwin. And the intent of saying it, bringing in together the contextual awareness. I have actually put a hint, which was supposed to come later, but it's coming out right away. It's the term called location intelligence. So the idea is we have been using maps, and I think we all know that maps had their own history, where we used to look at a map drawn on paper, while today we are a part in the map. That's our history in maps. And this is where the location of GIS maps is how we can bring this together with the physical assets and the spatial relation between the processes and the objects is a very interesting aspect of the digital GeoTwin. And to make this simple is when I'm talking of air quality, we can understand that we are not going to talk only about the AOD particles in air, the PMD 2.5 particles in air. We're also going to talk about the wind. We're also going to talk about the direction of wind. What are the surrounding geospatial elements in it? So this digital GeoTwin warrants for a location intelligence uh, platform that is to be used. A very interesting question is, and Dr. Vidam said that, Danny, can we speak of some applications? I have just listed a few applications for your reference, but if you all are with me so far, if you realize that if you look out of your window, or if you look out of your door, or if you walk out of your house, everything and anything falls under the digital GeoTwin. because we are talking of the geospatial world around us, where we also are part of it. But just to name a few applications to get your attention, we're talking of infrastructure and utilities, transportations. This is called as metaverse city, and there are many names. We started with smart city, future reference city. Now we are talking as metaverse city. We can talk in terms of tourism or even space exploration. Well, that's exactly from where it was born, and it has also gone in the diverse industries in healthcare, in disaster, in mining, in marine, and I promise you, the list does not end here. It is just what all you could see is part of it, right? So to give a further view of this, and that is what we call a future ready city, which I have shown to you. If you now realize in the bottom part is the physical world, right, which is visible here. And anything and everything that we see, we look, we experience is the physical world, right? To this, then we have sensors, when we have actuators that are collecting this data, we are pushing it to the data center, and that is what relates to the virtual world. So the essence of me talking for the last 10 minutes is trying to give a very fundamental definition to you all, is that we want the physical and the virtual world coming together, talking to each other, exchanging data with each other. And now you could relate this to any and every use case aspect that can come to your mind, which is to do with the digital GeoTwin, right? Because we are essentially saying that, hey, I have a virtual twin, and twins are nothing but we call in Hindi as judwas. So the twins are nothing but the real world twin that I have in my virtual space. How can I use it? So that is what the essence is. Now, having talked a bit about the digital twin, I wanted to call out the classifications, the broader classifications. So there was a paper that was published in 22. There was the first attempt to build a standard framework called DUET. And in this, they gave a very simple definition that we'll have a lower level digital twin and an advanced digital twin. And when I speak of the lower level digital twin, it is basically just the connect between the two and the virtual representing the actual physical element, which could help to understand its dynamics, its current states, and its future states, right? Now, this is a very basic digital twin over and above 3D model, where we have the geometric representation and the attribute representation on top of it. But the real crux with the advancement in technology of the last 10 years, is where we now bring in, bundled with artificial intelligence, is where we want to have a predictive model to help us, not only help us understand what decision we should take, but can it take decisions on its own? I know it sounds scary at times that if the machine does everything, then there's still a problem. But given the space and the dimensions, we can always have our restrictions laid on how much we want the machine to take the calls, right? So this is where we want to advance. And I'll take a reference from S3 from the industry, where RGS is one of the tools that they have, and you could see the maturity models. So from a geometric twin to an interactive twin, moving towards predictive twin and then to an advanced twin. So far, I've been harping on the geometric twin and the interactive twin, where the data is exchanged on the 3D space, and the interactive twin is a platform where I can see what is the analytics on top of it, that I could see that what was there 5 years back, what is now there, what is the trends, what are the analysis, the dashboards and the reports that can come out. So that is where the interactive twin comes to play. But we would like to mature further, and we take this opportunity to talk a bit more. And that is where we're going to talk more of the predictive twin. And in the predictive twin, we are talking of forecasting, and we're also talking of simulation. So I think with that, I would let pause here, and I'm sure we'll have time for more Q&A later. So that's all from my end. Thank you. Over to you, Dr. Vidama.
Thank you, Danny, for giving us such a simplistic view of what a digital twin is. and how a digital twin in an Earth reference, which I call as Geo-Twin because it's the twin of our Earth systems. It's related, and the different maturity models you have talked about, like just from a view and a query and interact and understand our space to actually model and analyze it, and have a self-learning capability inbuilt into it with the new technologies like AI, machine learning, deep learning, all these technologies. So we move on to our next speaker, that is Ms. Priyanka Talwar, and she is currently research associate at IIT Mumbai and IIT Bombay, and also pursuing her PhD in the same from the same institute. Her research focuses on the intersection of computer vision and remote sensing, where she develops innovative solutions for analyzing and interpreting geospatial data with expertise in cutting edge AI technologies. Priyanka is passionate about advancing the use of deep learning in remote sensing applications. Over to you, Priyanka.
Thank you so much, Dr. Yogita. So good morning, everybody. So here I will be taking you how this digital GeoTwin, we do the simulation and how the prediction works. So simulation is the visualization of prediction. So first we will be using some models to predict the data and how actually it would look like. We will simulate it rather than having it in the real world, implementing directly. We will have the simulation. The next slide. Yeah, so we have a demo video. Let's have this video. Danny, can you just play that video?
Yeah, just a minute, ma'am. I think I had only kept the presentation on, so just a minute. I'll change it.
Yeah,
Sorry for that.
okay.
Do that right away.
No, you just
Let me know if
you're
visible now.
sharing the slides, no? So you
Visible?
share the slides and then yeah. Yes. So no matter where in the world you live, so the city generates more data from the flows of people and goods. And like, but lots of data doesn't necessarily make a city smarter. Rather, we synthesize and fuse this data, helping it making a sense so that it is making a digital twin for your city, including people, streets, buildings, and every objects. So digital twin generates same patterns of movement and activities as a real city does. Just we are twinning the actual real scenarios because their underlying attributes and behavior are just similar what real time people do, what we are doing. So we will be simulating, and the question comes, what if what we are doing, and it makes a better decisions in designing this digital twin or to anticipate and benefit what events or when the technology would disrupt and what will happen if the disruption happens. So for the data-driven, human-oriented, we're designing this digital twin. So yeah, that was a very short video from Geo-Twin. Thanks to them for creating a wonderful video. Now let's move. So as I told you, what if? So digital models, digital geo models generally give or always give us the answer of what if, what happens. So we make assumptions, or we make the prediction models using different technologies. Before AI, there was some physics method, some other different methods. So what if answers the prediction to visualize it, and that visualization we call it as simulation. Next, please. Yeah, next slide, please. So in the predictive modeling, I will be discussing three. What are the three? I'm majorly focusing on one of them. So physics-based models. So as the name says physics, so we would have some differential equations, some different laws of nature, Newton's law and other laws, which will help us to predict what could be the future. or what could be the circumstances for the instance. That is something a theoretical thing, which will involve time, space, and causality. What will happen if this thing is being implemented or this climate change happens? So, how it will affect the human? How will it affect the animals? How will it affect the environment, and so on? It's very computationally heavy, these physics-based models, since we have the differential equations, and as we know, differential equations have heavy computation. So to reduce this computational efforts, we reduced order models were introduced where dimensionality was reduced. And reducing this complexity, it would help us to speed up the task. And this was done with the machine learning algorithms and machine learning models. So this reduced order model is a blend of physics based with the machine learning aspects into it. How quickly we can do without wasting much time, having less complexity, and speeding up the task, and predicting what could be the actual scenario if we give some inputs to the system, to the model. Next, now, next slide, please. Danny, please, next slide. Yeah, thank you. Back the probabilistic graphical model.
Yeah, actually, there's some lag in your seeing the screen. So,
Okay.
Danny, can you go to the previous slide? Yeah.
Yes, thank you. Oh, I hope, yeah. So basically, we would be focusing more on this probabilistic graphical model, which is now into picture, and it is an integrated of the calibration, data assimilations, planning, and how the things work. Actually, how the things work in the physical space is being passed to the digital space. Whatever we have at present, we pass it to digital and then make a prediction based on the actual state as well as what inputs we are adding to the system. The physical state, as its name says, like will have physical state, how the things will look like. We have the control inputs. I will give an example in the next, you can say that slide or something similar. And then what is observational data from the actual state? While twinning it, we will have the digital state, yeah, how the things would look like, quantities of interest, and the rewards. Rewards would be if it actually what we have predicted or our model has predicted, will it actually be there or not? It's the rewards, and if it is a positive reward, and if we have something negative reward, that is if the prediction is wrong, then we will have the negative reward, and then we can train back our model. So predicting in digital space and with some parameters with time, and based on it, we will be just looking at it. So the T here symbolizes that at time instance, because at every time, whatever we are inputting, it would be for that instance. As, since the parameters keep on changing, and it's not a static, we are working with a dynamic situations. Yeah, so here comes, like you can see on the left hand side, we have the digital states and the digital era, and on the right hand side, we have the actual or the physical state. So as you can see, how the physical state has, it has parameterized state of physical assets, what actually the aeroplane blade looks like. We just need to do it as a twin. So similarly, we have observational data, how the information is describing that particular blade, how it looks like this. Let's say it's very simple example. Let's say it's a 10-meter long, or it's 3 meter wide, and some one, let's say 1 centimeter or 2 centimeter in width or so. I'm just taking the rough examples, and then so this is actually how the observational data is. And then comes the control units, what actions and decisions we need to do, what we are having in the physical asset. That is in the physical state, what actions we need to do so that it is not withered. Similarly, we need to imitate in the digital twin system. That is a digital state. So what digital state it would be? Digital state would define how computationally this model will be the same as a physical state, right? And based on that, we would have the quantity of interest. Quantity of interest would be describing how the assets would look like, how estimate what we have the model or what we want as a output, how estimated it is. Based on these quantities, we would have the performance of the system and the rewards would be given. And this will make as an asset twin system. Let's take a very simple example, like let's have a nuclear reactor. So nuclear reactor, the combustion is happening every time. And combustion needs to be in controlled manner. If not in a controlled manner, the nuclear reactor could burst out. So parallelly, having the combustion and the cooling part goes one on one. It's not like that combustion is happening, and when it's reaching at its peak, then we start cooling. No, it might not reach to the cooling part peak, and it may blast off. So this comes as a control unit. We need to control both the combustion as well as the cooling temperature, right? So combustion and cooling are in control, then temperature can be predicted. What could be the possible temperature for that instance? So, for example, if I say what could be the casualties or what could be the quantities of interest? If power fails, then the cooling unit stops. Then what will happen? Combustion is progressively growing, and the temperature is falling. It's not working, it's not cooling. Then there could be a point where it could burst out. So for this situation, we need to predict when this situation can arrive. And this comes into picture when digital twin will help us. That combustion and cooling would be the parameters which will be keep on changing so that it won't hamper our actual model or actual system in place. So we will simulate this. We are thinking of this. We are formulated out after this much of combustion and the cooling stops. This can be done. Accordingly, we will simulate the situation and try to make the model learn so that the cooling and the combustion takes place hand on hand. So it is not hampered or the nuclear reactor doesn't blast off. So next slide, please. Yeah, so here you can see that predictive modeling, specifically, if I talk about a probabilistic, uh, the models which we are working on, it works on the Markov chain. And uh, Markov chain thing works with the time instances. What is the present instance? What is the something which we have done previously, just before? What could be the next step, right? So to have the next step, we will have it in something similar manner, right? Oh, yeah, I can see the slide now. So what is on the top is the physical state and what is bottom is the digital space. So whatever we are having in the actual, we are just making as a digital twin. So as you know, there you had something similar like in the physical space, that physical space, observation data, and the actions need to be taken, right? In the digital space, what do we have in digital space? Digital state is having the digital space, and then we have the quantities of interest and the rewards. So here D represents your digital space, Q represent your quantities of interest, and R represent your rewards, which is on the bottom hand side. If I talk about the top thing, that is your physical state, S, observations, O, and U, the actions needs to be taken so that in the next state, what could be the possible thing so that we can help our model not to hamper. So it's given like timestamp 0, then timestamp 2, then timestamp 4. What would be the possible things? If I talk about this, is acting actually the similar how the Markov chain model predicts, right? So present the second one, the prediction. Then when it is predicted, so last two instances we will take into account, and then based on those outputs, we will forward the next one. So if we say the physical space and the observational space, we are moving that physical space to S0 to S1. We are forwarding the input, and then from S1 to S2 we are forwarding. Similarly, the observational units are being taken into picture, and based on that, we are moving forward. If I talk about the digital space, the same inputs, observationals, and the actions are being given, and how to imitate the actual scenario. And then the digital space and the quantities of interest will decide whether this reward need to be given or not. Actually, what is present and what we predicted, is it matching or not? It matches, it gets a positive reward, and if it doesn't, we need to retrain, and then it gets a negative reward, and it's learned into the next phase. Similarly in D1 phase and then D2 phase and so on. Yeah, next slide, please. So here the use case of digital twin would be, so like as of I told you about that combustion of the nuclear reactor. So it's just automating the things with the virtual inspection. So here comes a picture, is whatever our mathematical model, the probabilistic graphical model is predicting, we cannot implement it directly in the real world scenario. Rather, we will need to simulate it, have some model which can just act as a real time thing, and then we can just see whether what we are thinking, what actually is going to happen, will not hamper the real world scenario. Let's talk about the combustion nuclear reactor. We cannot wait for the nuclear reactor to burst, right? We need to simulate it and check when, at what point the combustion is there, and at what cooling temperature is not up to the point that the nuclear reactor is bursting, so that we can have some similar conditions. If similar conditions arises in the real time, we can have a control on it and save a real time thing for the nuclear reactor to not to burst or not to blast off. So digital models are always like yes. So they are just based on the simulation. So simulation accurately like simulates what events are going to happen, or what systems or the processes are going to happen. Here, if I talk about it, we have three major things. One is object, then one is another is system, and the third is process. Object is what is affecting, what is the effective part. Let's say here in the example of nuclear reactor, we have the combustion thing. Then we have the system. System is what is the actual scenario where we are implementing. So here could be the nuclear reactor. And what is the process? How the effect of the object is on the system. I can take another example. Let's say we have a forest. Then forest would be a system. In this forest, how the wind is blowing. So this wind would be my object because it is affecting the forest area. And the process is how the effect of the object, the wind, is affecting my system, that is affecting the forest. How the system would react on the parameters of the object. And this is how it's moving along the flow. Right? Now, two things, the prediction model and the simulation model goes hand on hand. So here simulation, we need to have to analyze the alternative solutions based on the simulation results if something goes wrong, or we have met the threshold. Up till here we will do this. If it goes beyond the threshold, we need to be like check again the what are theoretical or the differential equations were, and then tuke our parameters and accordingly simulate again, so that the worst things never happen in the real world. And due to this worst thing, like nuclear reactor doesn't burst, or we can prevent forest fires, we can have the prevent the drought situations. So this will help us in while simulating. We do not go below the threshold, or the threshold is the bottom one, or we do not go the threshold above one. So to save the actual environment. Let's say example are predicting the effects of climate change. If the noise pollution is increasing, how could it affect the climate? So we cannot wait for that noise pollution to reach a peak and then change that climate and then affect the environmental thing. We can simulate the model and we can visualize the things so that we can take the preventions before it is going. Something like self-healing process, or like you can have the supply chain and the prediction of the events of the hazards happening. Crowd management is, and the location intelligence is one of the good example. Suppose you guys are traveling and all of a sudden one bridge for breaks up and the maximum traffic is over there. How to manage the crowd? We cannot wait for the bridge to fall and then check how we will manage. Rather, we will simulate if this road get blocked, how we will manage the routes or how we will reroute the traffic and do the things. Same exactly like location intelligence. We have the GPS systems, and if something fails off, how it could divert to the another thing. Yeah, the next slide, please. So now comes the agent-based simulation. So you might have understood what agent, like with the example. So agents is something where actually people or some objects come into picture which are living. Like we could be the agents here. So agents could be we, the people, or group of people, or number of entities here. And just remember, data here is never static. We have the dynamic data, we have the real-time data. So people would be coming and going. And we need to make the digital twin, the digital geotwin, I would say more specifically, digital geotwin, how actually the scenario is for that city, for that street, or whatever we are capturing. Or we can capture it for inside our house also. How the things are working, how we are moving in the house. Then comes the sensors. So where appropriately the sensors which sensor needs to be installed, and the data. Based on the sensors, what data needs to be collected from the objects. Whether if suppose let's have it in our house, so these sensors would be, let's say, temperature. Coming, suppose in a room, we are geotwining a room when we have one human being or two human beings or group of people are sitting or some animal is sitting. At different times, the sensor will keep the temperature readings and we will form it as a data. And based on our problem statement, we will take these temperatures at different situations.
Hello. Did we lose her?
Yes, we lost her.
Actually, we lost her. Yeah. So yeah, and she's in a place where the network seems to be a little tricky.
Yeah. So
Yeah.
can you take over from here?
Yeah, I'll take over from here. So I think
Yeah.
she's just calling me. I think I should. Yeah. Yeah, she's joining in a minute. She said I can still go ahead. So the view
Yeah.
that we had, and I think while I'll just take over for a minute. So the essence that we're drawing in the agent-based simulation is to get the information related to the object in consideration or any object that's around the space is where we have a counterpart called agent in the simulation itself, right? And when I speak of the agent-based simulation, you may now realize that an agent is the conscious being that is making decisions or taking actions, interacting with other agents and the system and the process and also the environment, right? So that is where the definition of the agent lies. And this agent need not be an individual. I think she's back, so I wouldn't like to take away a show. Yeah. Priyanka, ma'am, you're back.
Yeah, sorry,
Priyanka, ma'am, can you hear us?
it got dropped and yeah.
Yeah, so I
Can
just
you share the
did it.
screen?
Yeah, I've shared my screen. I was just giving the definition of agents, and you can take it up from there, ma'am.
Yeah. So agent based simulation. So if you give the agents, what could be the agents?
Yeah.
Yeah, I
So
guess it
you can
dropped
go ahead
down.
from this slide. Yeah. Yeah. Hello, did we lose her again?
Guess so. There
I
are
think she's gone
issues.
to, I think she's gone to the transformer and then back again.
Yeah, she. So
So I
you
think
can.
I'll go ahead with this. So
Yeah.
basically, when we speak of, and I'm just covering for her, is once we have this agent definitions, that is where we follow the behavior of the entities in this system. And that is what I think, Priyanka ma'am was trying to call out, that this is not a snapshot of an event. This is a continuous, time that we are looking into. It is a continuous process, not a discrete timestamp that we are talking of. And that is why the agent-based simulation is such powerful, and it also means a lot of things need to be considered in it, right? Again, with each aspect that comes in and every update that comes or the time pass that goes on or an event that triggers, it would mean that the system would apply forces, bring in triggers or bring in a change in the behavior of the agent. So this is where the agent-based simulation plays a very powerful role, right? And finally, what we did is we put an example here for your reference. Is that when we're talking of transportation systems, urban planning for transportation, you can see that bring in the properties and constraints of the urban transportation systems that we need, and also bring in the human behavior into such predictions, right? And a very simple example that we can give to you all is when we speak of autonomous driving, and when I'm crossing a crosswalk. Now, whether I see a pedestrian, a human, is the person walking or is the person standing? Also make me to decide what should be the behavior of the vehicle, of that object at that point of time, right? Should it shift lanes or should it stay in the same location or should it stop? Basis how the other agent is moving, how are the other parameters in the system? So agent-based simulation actually really helps. And my way of saying is, we as humans have this tendency that we need one of our senses to validate it. A formula and the results do not help us, but we need some of our ways, of our senses, and visualization is the best. And that is why I believe, the agent-based simulation is really one of the best ways to validate the predictions, validate the alternatives, and validate the what if question, which is being answered by the digital GeoTwin. So that is where we would like to pause for the simulation. Taking you to the other aspects, we've been seeking all the good things, but there are challenges. Right? There are always two sides of the coin. So we also have challenges in the predictive modeling. And as simple as this, right from the input that we spoke of initially of standardization, collection of the data, defining of the sensors, handling such a huge amount of data, processing it, and then also defining the output, which requires a lot of validation verification. And this also brings in an inconsistency as to what is a smart solution or what is a safe solution. The quantification also changes from use case to use case as well, right? And finally, while we are in the world of AI also has its aspects of data, of computation, of resource needs, of the GPUs and the CPUs that we talk of in the world. So everything has to be kept in mind while we perform the predictive modeling and the simulation for them, right? Finally, taking one more step behind is we speak of the challenges of the digital twin or the digital GeoTwin that we spoke earlier. And you could see very well, you could relate it now to the right-hand side of the space, where we are building a virtual layer of a digital GeoTwin, right? Which is mapping to the real world. Which means while I'm saying that I'm bringing the two worlds together, connected or interconnected and interoperable, it would also require that we need to understand the hardware aspects of the story, the data management part of the story, and the software aspects of it, right? So yes, it is something that we all see in our sci-fi movies, and we all have read about it and have tried to work on it, but there are challenges that do come up, and they are with respect to the expectation setting. They are with to do with the data, the normalization, the standardization of the data, the frequency of the data to be inputted, And that is where definition of ontology for a digital geo-twin to solve the specific use case that you're looking for has to be very well thought through to understand how we will be able to successfully define, build, predict, and simulate the digital geo-twin. So with that, I'll hand it back again to Dr. Yogita ma'am because I think we are now open for Q&A. But I'm sorry I missed the conclusion slide. So I did speak of it.
So
before.
we can let let Priyanka conclude it because she's back.
Oh, she's back. Yeah.
Yeah, I'm sorry.
Yeah.
I'm so sorry. I don't know how it is dropping off in the middle. So sorry. Yeah, so let's conclude. So, as Danny discussed and some parts I discussed, so digital twin is now the most emerging technique or emerging technologies which are coming into picture because we are digitizing the world now, making it as a twin, just replicating it, or the anything we are replicating. It could be the tables, the fans, the mobile phones. Now we are moving into one more step inside. That is, we are geo-twinning. Whatever actually is on the earth, we are just geo-twinning and then simulating, predicting, making prediction models, and then trying to improve so that the environment is being affected. It's not affected what we are making cause different. So it comes into picture the sustainability concept. So we have to make our environmental sustainable, and we need to have the sustainable goals. So digital twinnings and specifically the geo digital twin will help us in making or improving the sustainability efforts. Also, a soft bed needs to be built up for a self-reliant, self-healing, and the self-learning system. This is a very most one of the most important point. We need to start implementing, and then looking forward for the collaborations and different based on the what earth is getting affected or what the environment is getting affected, making the climate change or sustainability goals are being affected. We need to just have a forward interdisciplinary, not exactly a computer science guy would be needed or a geographical guy needs to be. We need everybody here, like environmental also, chemical also, physics guy also, as well as somebody who can have the civil aspect and somebody who works in remote sensing. So it's an open domain. It's not restricted to one, like a sciences guy or arts guy or a commerce guy. We need everybody so that we come on a common place to protect our earth and have the sustainability goals being reached. Yeah, thank you. Now over to Dr. Yogita.
Thank you so much, Danny and Priyanka, for giving us a very simplistic understanding of digital geo-twin. First digital twin, then digital geo-twin, and how we can do the predictive modeling and simulation in a way that it is understandable to each one of us, how we can relate the real world scenario in a virtual world, and how the complex terminologies of the digital world, it can be simplified in a way that each object, each observation, it is put into the digital framework. And thank you very much. So I am opening the session for the questions and answers. I would request the audience to raise their hands, and if they have any questions, we can have those questions.
Yes, Dr. Yogita, I have a question.
Yes, please.
My question goes to Priyanka. I wanted to know, can we simulate the things? As you know, the air quality of Delhi is very severe and bad. So, can we do something with your simulation, and what will be the preventive measures like that?
Priyanka, you can unmute yourself.
Oh, I'm sorry. Yeah. So yeah. So my answer would be yes. We can simulate these situations. Whatever actual things we have, like let's say we have ppms, we have soluble matters in air, or some hazardous thing like we have nitrogen or more of oxygen, so which could be beneficial and which could be some let's say we have methane gas which could affect, or some I am not able to, like, let's say some chemicals which are actually affecting the environment. Those parameters we can have in a time series, and then we can simulate, and based on a predictive model, these prediction models will help us what could be the future instance. By increasing one and decreasing the another gas or another material or the particles present in there, we will have some model, and then we can simulate and see what could be the worst.
Yeah.
If I
So
I
can,
I
would
think,
also I would also like to add, like if we increase the vegetation cover, for example, so can that also be simulated in this scenario? Like how can that be done?
So
actually, just a minute. I'm looking for a very concrete solutions. So many people are providing the solution, but government is really looking a good concrete solution to reduce the air quality. So for that, is there, do you have any idea so you can discuss with me, and you can collect my number to Dr. Yogita.
Yeah,
Danny
Danny,
has spoken.
please.
so, Doctor, to answer your question, there was a study done in 2022, which was called as a duet, and it was done in Europe to understand the air quality. So, of course, there is a methodology attempted in the research and in the literature in 2022 in Europe. I presume we need to join hands together, and a short answer, a simple answer is yes. The long answer is we need to define the parameters around it and then build a digital twin to get the answer. So it is possible. Yeah. I think we can talk that offline as well.
So do you have any contact number? Please talk to me, and we are really looking for a good solution for this.
Sure.
Yeah.
Yeah, Aryan, please ask.
Actually, I have few questions, not one. So should I ask them one by one or like?
You can ask all of it, and then
So my first question is to Danny sir. Sir, what industries are benefited most from digital twin technology? Um, the next question is, sir, like what type of data is used to create digital twin? And sir, how does like real-time analytics will enhance the functionality of digital twin? These are my three questions.
No, I didn't have a beautiful memory. I forget the very moment you said it, but I'll go one by one. If I miss, you can correct me. Right. So the first one is what industries are benefited. Right now, one the digital twin that I'm referring to, the first page, if you recollect, and if you recollect the maturity model, I'll bring it back. I don't know if my screen is still share mode. So if you see here, Aryan, can you see my screen of the maturity model? Right
yes, yes,
now,
Yes.
please.
depending on the use cases and depending on the amount of investment that a particular industry would like to do, this is where the digital twins would benefit. However, as I said in the beginning, the digital twins are very vaguely used. Of course, in the industry 4.0, the chemical plants industry, the industry which is doing manufacturing, the logistics industry, they have already benefited from the digital twin. But is that a digital twin in its sense per se of a geodigital twin? No, it's more of uh, the data that it has resided to, the ontology that it has defined to. If you realize now, we are also expanding in the field of healthcare, where people are able to remotely diagnose. Rather, there are literatures of research where they have been talking of having a digital twin of a healthcare solution, right? But to give a short answer, this is applicable to every industry depending on how much is the element of investment and study that needs to go in, and the return of investment that's going to be back in the system. But to give you a short answer, Digital Twin platform has been successful. It is there in many different forms. Rather, what I show you is ArcGIS. We also have open source technologies that do support it. As a platform, it is used across the industry. But when it comes to specific use cases, that is where it is limited to a few industries right now, which I've already called out. But that is just not the end to it. And primarily, uh, the key if I had to take the key ones that come to my mind is, when you speak of the digital twin, we have the Singapore, we have one in New Zealand or Australia, and there's one more that was built as a smart city solution. And it's primarily the government that is trying to right now harp on it to build the sustainability model. So that's my short answer or a long answer to the first question you asked, Aryan. I hope I was able to answer that. Can I have a second question,
Yes.
please?
So my second question was, what type of data is required to create a digital twin?
Yeah, and this is again, it's the question is a little abstract. I'll try to make it a more straightforward answer. And I did use one of the terms called, the ontology definition, right? Now let's take the case where the doctor we just spoke of the air quality issue. Now, given the air quality problem, the amount of data would depend on what are the key uh, entities and the key subsystems involved in making that kind of issue, right? And that's what I think I gave a few examples of NO2, SO2, PM 2.5, AOD. And in AOD, you talk of different levels. You could also talk of moisture in the air. Now, that is when I speak of air quality. If you now take me into the space of sustainability of mangroves, my data elements will change completely. I may look at collecting data from infrared information, trying to identify how is the health of the mangroves. I would look at the air, and I would look at the air, I'd look at the water, I'd look at the soil. So the data is really essence to the problem that we are trying to solve. There is no single bullet or a silver bullet that solves this answer. But the data definitely depends on the type of problem solution that we want. And I'll give you a more easy example is when I talk of crowd management, right? In either malls or in terms of temples, you may talk of people, but I may also talk of vehicles. I may also talk of the road capacity, right? I may also talk of other aspects in the mall as to if there are any events happening, right, around it, surrounding it, which could be required to define the crowd management that needs to be applied. So, Aryan, I tried to keep it short to answer your second question of data, right? And again, in the world of ML, we have to normalize the data, which was also one of the challenges I brought to you, that we'll also have to normalize the data because the number of people, the number of vehicles, and the number of shops, we need to quantify them in a specific range. If I talk ML, -3 to 3 is a given beautiful range, right? So that's the answer to your second question, Aryan. I hope I was again able to make
Yes,
a
yes.
response
You
to your
also
question.
get my fourth question, which was related to challenges.
Yeah.
So my third question is, how do real-time analytics enhance the functionality of digital twin, like the real-time data and
So
enhancements?
rather, I will be saying that if you ask me and my personal opinion here, this is where the crux are. So if you look at all the research that you have done, I'll take an example to where I'm doing a research in urban flooding. We either are doing a pre-event or a post-event assessment. But when you have a digital twin, you are actually in the point of time, the point of case that you are into. Rather, it cannot be more beneficial than this, right? So today we are talking of using it as a test bed for what if scenario. But the place where you have seen in our third conclusion point that we were talking of a self-healing system, the real-time data would be the essence of building a self-healing system on its own, where the system decides on its own what needs to be done, rather than a human sitting there telling what needs to be done. I know it's a very controversial answer, but the real-time data would really mean a lot. But aren't that's easy said and done because collecting so much amount of data, the time lag that comes from the sensors, and relaying it. I mean, you may say that, and there are a few researches that I've read. They talk of we'll have to go in the 6G space to really have the data. When you say real time, in real time, coming to me, coming to the digital twin, doing the processing, and then making a result out of it. Because there will be many models running at parallel. So you can understand that I'm talking of a multi-tenant environment, having multi-messaging, multi-publisher, subscriber, multi-modals running at the same time, trying to solve the problem. But the real-time data would make a big difference to the entire equation. That's my answer to you, Aryan. Yeah. Hello? Did I lose
Yeah.
myself?
So thank you so much, Danny, for putting in perspective that how real-time real-time analytics, it's going to enhance the functionality of digital GeoTwin. Can do we have any other questions? I don't think. It was such a wonderful session today, understanding the nuances of digital twin, how it's related to a twin of our Earth systems, and how with the physics-based model and integration of AI, machine learning, coming together to provide the simulation and predictive modeling, it was really quite a learning experience. Thanks, Denny, and thank Priyanka for this wonderful session. And I would also thank all our participants to be there patiently till the end, and also for the questions which has been put forth. Thank you so much for joining.
Thank you all.
Thank you, ma'am.
Thank you all. Bye-bye.
Thank you, sir.
Thank you, Dr. Yogita, and
Thank
thank
you.
you for
Thank
this
you.
opportunity.
Thank you, Dr. Yogita, to provide such a rich, full content.
No, it's
It's a very good
pleasure.
initiative. Yeah.
Thank you so much.